Looking at another related rates problem, it says we have a 17-foot ladder is placed against a building. The base of the ladder is slipping away from the building at a rate of 9 feet per minute. Find the rate at which the top of the ladder is sliding down the building at the instant the bottom of the ladder is 8 feet from the base of the building. Okay, so this is where actually drawing pictures can be helpful. And so we have some building and we have some ladder that's going up the building. And we're given that that ladder is 17 feet long. Let's go back and pull out information. The base of the ladder is slipping away. So this is moving outwards. At a rate of 9 feet per minute. So maybe let's let this be the length. So X equals the base. Or we can say that's the same thing as the distance between the foot of the ladder and the building. Okay, so we are looking at it telling us that it is moving away from the building at a rate of 9 feet per minute. So we actually know what dx dt is. Given that dx dt is equal to 9 feet per minute. Let's see what else we have. Find the rate at which the top of the ladder is sliding down the building. And at the instant that the bottom of the ladder is 8 feet from the base of the building. Okay, so we know what X is. We want X to equal 8. We want to find the height or the rate of change that height is falling. So we want to find dH dt when X equals 8 feet. Let's see if there's anything else that I need to pull out of here. That's it. Okay, so we have to come up with some sort of equation. Let us say that H is equal to the height of the ladder. So we need to figure out what that equation is. Well, a couple things that we can do. We can use the fact that this is a right triangle and Pythagorean theorems. And so this was X in here. And so by Pythagorean theorem, we know that H squared, not our hypotenuse, I just called this as H for height, plus the base squared, X squared, is equal to the hypotenuse squared, in our case, 17 squared. Let me just pause for a sec. So we need to find one more variable, and we can do that because we know we can figure out what H is, what that height of that ladder goes up the building when this is 8 feet away because of that Pythagorean theorem. So I can say, I know h squared plus, I'm looking at when 8 squared is equal to, that ladder is 17 squared. So h squared is equal to 17 squared minus 8 squared. Well, 17 squared gives us 289 minus 64. Which is 225. And if we take the square root of both sides, and it wouldn't make sense to use the negative because we're talking about height, the square root, that's going to give us back 15. Okay, so we want to find, again, DHTT. So we're going to go through here. We're going to take our equation that we know. Our height, that's changing with respect to time, depending on how far that ladder is being pulled out. And so let's go through again and differentiate both sides. And our height is with respect to time and our base is with respect to time. So when we take the derivative of h squared, we get 2h dh dt. Plus the derivative of x squared, which is 2x dx dt, is equal to the derivative of 17 squared, which is 0. Well, we want to find dh dt. And we're given all those other values. We just found that h was 15. So let's go plug these values in. So we have 2 times h, which is 15, times dh dt, which we're looking for, plus x, 2x. But we know what x is. X is 8. Dx dt, we also know that was 9 feet per minute, is equal to 0. So we have 2 times 15, so we have 30 dx dh dt, plus 2 times 8 is 16. 16 times 9 gives us 144 equals 0. So let's get dh dt by itself. We would subtract 144 and then divide by 30. So we have 30 dh dt is equal to negative 144. So dh dt is equal to negative 144 over 30. And let's see. I think 6 goes into both of those. So 144 divided by 6, that gives us 24. So this is equal to negative 24 all over 5. And this is feet per minute. In our case, not per minute. So it's sliding down at a rate of 24 feet every 5 minutes. That's how fast it's falling at exactly when our base is 8 feet away from the base of the building. This negative 24, that's telling us it's decreasing, right? The rate. Okay, Okay, so the next word problem says a sand storage tank used by the highway department for winter storms is leaking. As the sand leaks out, it increases or it forms a conical pile. The radius of the base of the pile increases at a rate of 0.75 inches per minute. The height of the pile is always twice the radius of the base. Find the rate at which the volume of the pile is increasing at a rate. The radius of the base is 6 inches. Okay, so we got a lot going on here. So we have some tank. I don't know what the tank looks like, but let's just say that we have some tank in here. And that tank, we have a hole in it. And from that hole, we're getting sand that's coming down, dripping down, and it's forming this kind of cone shape. Yeah, but you get the picture, right? We're given that this right here is R, the radius of our cone, and we have the height. So again, let's go through and pick out information. Sand storage, it's leaking. The radius of the base of the pile increases at a rate of 0.75 inches per minute. Okay, so we have the rate that this radius is increasing. So let R equal the radius of the bottom of the cone. And we know that dr dt, that rate is growing, increasing at 0.75 inches per minute. The height of the pile is always twice the radius of the base. So this height, that's nice, is always 2r. We want to find the rate at which the volume of the pile is increasing at the instant the radius of the base is 6. So we want to look at this when R equals 6. And we want to see the rate of change of the volume. So we want to find dV dt when R is 6. So we need to first figure out what the volume of a cone is. And that is equal to 1/3 pi r squared. Let me just make sure. Times the height. Okay, so we have our volume. And we can go in here and we can take the derivative of both sides. So we're taking the derivative with respect to time. I could do this, but I would have to be using the product rule in here. But instead, we know that H, we were given that H is equal to 2r. So we could go in here and let's rewrite that just in terms of r. That will be taking the derivative would be much easier if we do that. So we have 1/3 pi r squared times 2r. So we just rewrite this. So this is the same thing. And I'm going to rewrite the coefficient out front. So 2 all over 2 pi all over 3 times r squared times r, which is an r cubed. So now I've got it in the form where I can take the derivative of both sides. So derivative of v is 1 dv dt is equal to our coefficient 2 pi thirds times the derivative of r cubed, which is 3r squared dr dt. Notice our 3's cancel in the numerator and denominator. So we're left with 2 pi r squared dr dt. But we know what the rate of change is for our radius. And we know that we're looking at this when our radius is 6 inches. So we're just going to go in here and we're going to substitute it in. So we have dv dt is equal to 2 pi times r, which is 6 squared, times dr dt, which we were given was 0.75. So the rate of change of that volume is 6 squared, which is 36. 36 times 2 is 72. And 72 times 0.75, that gives us 54 pi. And this is at a rate of inches, cubic inches per minute. There's a rate of change of our volume when this hits 6. So let's look at some memorization skills. Under certain conditions, a person can memorize W words in T minutes, where WT is equal to negative 0.02 T squared plus T all over the quantity T plus 1. And we want to find the rate of change of words per minute, dW dt, when T equals 5. So all we need to do is go through here and take the derivative both sides. It's a little, I don't like that they did T. Okay, I guess it doesn't matter. It's just that we're taking a derivative. Stop for a second. Maybe it isn't as easy as I thought. Okay, so let's just go through and take the derivative using the quotient rule. So if we take the derivative of the left-hand side, we have dW dt is equal to derivative. So I need to use my quotient rule. Derivative of my numerator is going to give me negative 0.04 T plus 1, all times the denominator, T plus 1 minus the numerator, negative 0.02 T squared plus T all times the derivative of the denominator, which is 1, all over the denominator, t plus 1 quantity squared. So we need to distribute and combine like terms if possible. So we have this negative 0.4 t times t. So that's a negative 0.04 t squared. This gives us minus a 0.04 t plus t plus 1. And now let's distribute this negative. And so we would have plus 0.02 t squared minus t all over this t plus 1 quantity squared. So combining like terms, I have a negative 0.04 t squared plus a 0.02 t squared. So that's going to give me a negative 0.02 t squared. Here I have a negative 0.04 t plus t minus t. So actually we'll be left with a negative 0.04 t. And then I have this plus 1 all over t plus 1 quantity squared. And we want to find this when t is 5. So we're just going to go in there and substitute. So dw dt equals negative 0.02 times 5 squared minus 0.04 times 5 plus 1 all over 5 plus 1 quantity squared. So 5 squared is 25. 25 times 0.02, that gives us 0.5. So we have w dt, that equals negative 0.5 minus 0.04 times 5, which is 0.2 plus 1 all over 5 plus 1 is 6 and 6 squared is 36. So I have a negative 0.7 plus 1. So 1 minus negative 0.7 is 0.3 all over 36. We tend to not like decimals inside a fraction, and we can get rid of that by multiplying by 10 over 10 to move that decimal over once. So we get dw dt is equal to 30 over 360. Now let's reduce. So 3 over 36, which gives us 1 over 12. And they have that in decimal form, so let me just put that. They get negative, or no, they don't. I get dw dt. I need to make sure I did everything right, is about 0.08. So the rate of change and the number of words memorized when t is 5 minutes is approximately 0.08. Okay, so knew something was off. It's right here. When I'm multiplying by 10, that moves my decimal over once, which just gives me 3. And so it's 3 over 360, which is 1 over 120, which should give us 1 divided by 120. Yeah, that extra 0. So it's 0.008. There we go. Okay, so that is related rates. And like I mentioned, this was the last of derivatives. And on Thursday, we're going to get into the next chapter, which is antiderivatives. So we're going to look at integration and what that means.